Good morning, all the students. We'll start our next lecture. That is lecture 5 under module 5. Okay, in the last classes of basics of sampling theory, we have handled concepts on error estimation and estimating the binomial proportion, while estimating the true error and the sample error, how they tend to follow binomial distribution. And with the help of binomial distribution, how can we find the probability of the true error when given the sample error, that we have understood. And also we have discussed in detail about mean and variance. How mean, that is the expected value of a random variable, and the variance will impact the true error and the sample error, and the estimated bias. The difference between, if we can reduce the difference between the true error and the sample error, how you can make a model as having an unbiased estimate. Okay, that we have seen under estimators, bias and variance. Now in this class we are going to cover on confidence intervals and two-sided and one-sided bounds. Okay, when you are performing your hypothesis testing, what is the confidence interval within which the sample error may fall, the true error may fall, and outside which you may want to take some risk. Okay, that will be determined by stating a confidence interval. And two-sided and one-sided tests, whether you are applying bounds on both the sides, lower limit and the upper limit, or whether you are applying bound only on one side, only on lower limit or only on the upper limit. Okay, all these will be made clear in today's class. Now, one common way to describe the uncertainty associated with an estimate is to give an interval within which the true value is expected to fall, along with the probability with which it is expected to fall into this interval. So what is a common way to deal with uncertainty? What is uncertainty, first of all? Whenever you are training a machine learning model, by taking a sample and training a machine learning model on that sample, you always have a doubt that whether your model will perform in the same way with the unseen data also, or with the new data points also, right? So what is the doubt you have? What is that uncertainty you have? Remember, predictions are always uncertain. You are making a guess based on the historical data, based on the previous data, based on the training data. You are trying to guess what would be the value of some unseen data, right? You're just guessing it, you're estimating it. That is why whenever you are estimating something, always there is an error associated with it. There is some uncertainty associated with it. You're not certain in the predictions, right? There is always some uncertainty associated with the predictions. Now this uncertainty with an estimate, how to define this, how to describe this uncertainty that is associated with an estimate. It is to give an interval, means within which the true value is expected to fall, within which the true predictions expected to fall, along with the probability with which it is expected to fall into this interval. So what would be the interval and what is the probability of the true error falling within this interval? Say when I tell I have 95% confidence interval, I have assigned 95% confidence interval. In that case, I'm saying that according to the sample error I have obtained, I have confidence that 95% of the time, even the true error also follows the sample error, right? That is called as the confidence interval. 5% of the time, I'm not sure whether the true error will be same as the sample error. 5% I have some estimation error. 5% I'm uncertain about the true predictions that are going to be, the predictions that are going to be made on the unseen data. Okay, 95% I'm sure that the predictions would be correct, but 5% I'm uncertain about the predictions to be made about the new data points. by the machine learning model, right? That is called as the confidence interval. 95% I have confidence. So the confidence interval here is 95%, right? So what is the formal definition for this? An n% confidence interval. In this case, we are taking it as 95%. Sometimes we may take it as 80%. Sometimes the confidence interval may come down to even 60 or 65% also, if at all there is large variation between your sample error and the true error. Okay, so an n% confidence interval for some parameter p is an interval that is expected with probability n% to contain p. What is p here in our problem? The p is the true error. Okay, the true error is guessed to fall in this n% confidence interval, 95% confidence interval. Other 5% of the time, we are not sure about the true error, whether it will fall in this interval or not. It may fall outside this interval, which will show large variation between the sample error and the true error, indicating that 5% of the time your machine learning model is not performing well. It is making wrong predictions. Okay, did you see how all these terms are getting related? Accuracy, error, sample error, true error, all these we are roaming about only these terms again and again in order to understand the machine learning concepts. Did you observe that? Okay, now for example, if we observe R equal to, for example, if we observe R equal to 12 errors, means out of some 40 sample points that are given for prediction, 40 data points, 40 new data points that are given for prediction, 12 prediction errors are made and 28 of them are predicted correctly. Okay, so the number of errors made here is 12. Now, we can say that approximately 95% probability that the interval contains the true error d of h. Now what is the interval? 0.30 plus or minus 0.14. Do you remember how did we get this? It is nothing, the expression you remember? Sample error associated with the hypothesis plus or minus the critical value Zn, the Z value given with the probability. They are given in a table. For 95% confidence interval, Z value is 1.28. For 68% confidence interval, Z value is 1. And for other probabilities also, the Z value is given in the table. Do you remember that? So that critical value multiplied by sample error into 1 minus sample error divided by n. Okay, this is how you calculate the interval. Okay, this interval is 0.30. That is the sample error. How did you get the sample error? R by n. How many errors were made? 12. Out of how many data points? 40. So the prediction number of prediction errors 12 by total number of data points 40 will give you 0.30, the sample error. Okay, plus or minus with this 95% confidence interval, what is the Z value associated? 1.28, right? So 1.28 multiplied by 0.30 into 1 minus 0.70 divided by 40, you will get this 0.14. Okay, so that interval we are taking. Now, out of all these errors, we can say that out of these errors made, we can say that approximately 95% probability means the confidence interval we are taking as 95%, that the interval 0.30 plus or minus 0.14 contains the true error d. Means it falls within this range 95% of the time. Okay, this interval is nothing but this one. 0.30 plus or minus 0.14 is this interval. It falls 95% of the time within that interval, and 5% of the time it may fall outside this interval. Means the error may be too low or the true error may be too high. But most of the time it will follow this normal distribution. 95% of the time it will follow the normal distribution. It will fall within this range. Did you understand? So the interval how to calculate is given by this formula. Sample error plus or minus critical value multiplied by square root of sample error into 1 minus sample error divided by n. Got it? So that will tell you the interval into which 95% of the time the true error will fall into. Now, how can we derive confidence intervals for true error? Okay, we understood how to derive confidence interval for sample error. Now, how to calculate the confidence interval for true error? Now, the answer lies in the fact that we know the binomial probability distribution governing the estimator of sample error. Means we understood that as you keep on increasing the number of samples, then the sample errors tend to follow a normal distribution. And for simplicity, we have assumed that this normal distribution is approximately equal to the binomial distribution. Binomial distribution is almost following the trend of normal distribution. Okay, so we understood from this that the sample error is governed by the binomial distribution. Right? So the mean value of this distribution is true error. The mean value of this binomial distribution is the true error, and the standard deviation is given by the equation. This we have derived in the last class. You remember the standard deviation of the sample error. How do you calculate that? It is approximately equal to square root of sample error multiplied by 1 minus sample error divided by the total number of data points in each sample. Okay, so that will give you the standard deviation. The mean of the true errors, the mean value of the binomial distribution is given by the true error, and the standard deviation is given by the standard deviation of sample error. Okay, therefore, to derive a 95% confidence interval, in order to get the 95% confidence interval into which the true error falls, we need only find the interval centered around the mean value, that is of the true error, which is wide enough to contain 95% of the total probability under this distribution. Now we have assumed that an unbiased estimate value of a sample error is nothing but it is equal to true error. When there is no difference between the sample error and the true error, then we call that is an unbiased estimate. Sample error is an unbiased estimate of the true error because there is no difference between them. Sample error and the true error are the same. When there is no difference between sample error and the true error, we call it as unbiased estimation of the sample error. Okay, because both are equal. In that case, we can say that sample error is equal to true error. Therefore, to derive a 95% confidence interval, we need only find the interval centered around the mean. So for a normal distribution, this is the mean, right? This axis is the mean. Mean value of true error, which is wide enough to contain 95% of the total probability under this distribution. So this 95% confidence interval is actually wide enough to make most of the true errors fall in this particular range. Means you have made your machine learning model as ideal as possible so that this confidence interval is increasing. Now, if you say the confidence interval is 98%, if you say the confidence interval is 99%, then the confidence in your machine learning model is increasing such that you say it is highly generalizable. Means it predicts very well with the unseen data also. There is no difference between your sample error and the true error. it performs with 99% accuracy with the sample, and the same accuracy can be seen with the true error, with the unseen data also. Then we call it as high confidence interval. We say that the machine learning model has high confidence interval. Machine learning model means the hypothesis. When I say machine learning model, it is the hypothesis. When I say hypothesis, it is the machine learning model you have developed based on the hypothesis. Okay, do not get confused. So when I say that this hypothesis is performing very well, it is having large confidence interval, then I'm saying that my hypothesis is highly generalizable. It performs very well with unseen data also, not only with the training data. Got it? So this provides an interval surrounding the true error into which sample error must fall 95% of the time. Or alternatively, this provides an interval surrounding the sample error into which true error must fall 95% of the time. Either way it is true, right? 95% of the time, you expect that true error should fall into this particular interval so that it is in accordance with the sample error. Now for a given value of n, that is a confidence interval, how can we find the size of the interval that contains n% of the probability mass? Whenever you're taking continuous functions and guessing, whenever you're taking continuous values and guessing their probability, then it is called as probability mass function. When you're taking discrete values, I'm really sorry. When we are taking discrete values, in that case, the probability associated with them is called as probability mass function. But when you're taking continuous values, in that case, the probability associated with them is called as probability density function. Okay, now we are taking here discrete values of the confidence interval. That is why we wanted to calculate, or we wanted to find the size of this probability mass. For sufficiently large sample sizes, the binomial distribution can be closely approximated by the normal distribution, right? If you keep on increasing the sample size and if you keep on repeating the number of experiments, in that case, the binomial distribution can closely be approximated, or it can almost follow a normal distribution only. Okay, so what is normal distribution? It is a bell-shaped distribution. It is like this, right? Normal distribution. It is a bell-shaped distribution, fully specified by its mean. This is its mean. Here the mean value is equal to 0 and standard deviation sigma. And in normal distributions, the sigma value, that is the standard deviation value, will be equal to 1. Whenever you take a sample to follow normal distribution, then its mean will be equal to 0 and its standard deviation will be equal to 1. Remember this. Remember this statement. Okay, so the normal distribution here we have taken with mean 0 and standard deviation 1. Now it is a bell-shaped curve, it is a bell-shaped distribution fully specified by its mean mu and the standard deviation sigma. Okay, you know what is the standard deviation, right? How much does the spread of the data points differ from the mean average value? How much is the spread of the data from the mean? That is called as standard deviation, right? Now for large n, any binomial distribution is very closely approximated by a normal distribution with the same mean and variance. Now, if you take very small sample, your mean may not be equal to 0 and the standard deviation may not be equal to 1. If you take only 10 students data. But if I take 2000 students data of the college, in that case, if you keep on increasing the number of samples, if you keep on increasing the number of data points in a sample, then your mean tends to go towards 0 and the standard deviation tends to go towards 1. Means the variability in the data reduces. The variability or spread in the data reduces. Now I take say 1, 10 and 100. The variability in the data is very high. But if I take 2, 20, 200, then 3, 30, 300, 4, 40, 400, I keep on increasing the number of data points. Now you find the average and the standard deviations tends to become low. Why? Because I'm increasing the number of data points in my sample. Got it? The sample, when I take on 5 students, the variance in that sample will be very high. But I take the data of 2000 students, the variance in the sample will start becoming lower and lower. The deviation, standard deviation, the spread in the data will start becoming lower and lower. Okay, that is what we wanted to explain here. Whenever you increase the size of the sample, whenever you increase the number of data points in a sample that you're considering under a sample, then the mean tends to go towards 0 and the standard deviation towards 1, and entirely it follows a normal distribution. It tends to follow a normal distribution. Okay. Now the constant Zn given in this table, we know this table, right? For specific confidence levels, what would be the value of Z? That Z values are given here. I told you this kind of tables are available on Google. You can just type Z score table. You'll be able to find all the Z scores for given confidence intervals. Okay, so the here simple part of the table is taken for 50% confidence interval, for 68%, 80%, 90%, and so on. What would be the critical value that have to be considered? Okay, those are given here. Z score values are given here. Now, the constant Zn given in this table defines the width of the smallest interval about the mean that includes n% of the total probability mass under the bell-shaped normal distribution. So when I take a bell-shaped curve or my sample following a normal distribution, now if I take the mean and I consider the confidence interval as 95%, now this side it allows up to 1.96 deviation, and this side it allows up to 1.96 deviation, minus 1.96 plus 1.96 deviation, right? Up to that extent the deviation is allowed, standard deviation is allowed. That is why Z is called as the critical value, which helps us to understand what would be the variance in the data if you take this confidence interval. What is the tolerance of the critical value? Up to minus 1.96 and up to plus 1.96, you are giving a flexibility. Okay, that the value falls into this 95% confidence interval range. Now read this, the constant Zn, that is the second row values given in the table, defines the width of the smallest interval, plus or minus, minus this way, plus this way, smallest interval about the mean. This is the mean, right? This is mu. About the mean that includes n% of the total probability mass under the bell-shaped normal distribution, right? Now, more precisely, this Zn gives half the width of the interval. Half the width of the interval. Either it is minus or plus. That is why we have taken it as half the interval. That is the distance from mean in either direction. On minus toward backside, minus direction, or forward, plus direction, positive direction. Okay, measured in standard deviations, measured in terms of standard deviations. Okay, so when you take this as the mean, the center point as the mean, this critical value is taken as plus or minus 1.96 for the given confidence interval 95%, right? Now see here in this figure A, it illustrates such an interval for Z at confidence interval 80. What is the Z value at confidence interval 80? That is 80% confidence interval. At 80% confidence interval, what is the Z value? 1.28. So here, can you notice from 0, it has taken minus 1.28, and from 0 here the deviation is taken as plus 1.28. Okay, so you are giving this confidence interval and saying that 80% of the time with plus or minus 1.28 standard deviation, the true error falls within this limit, falls within this confidence interval. Did you understand? I'm repeating again, listen carefully. Whenever you take the confidence interval as 80%, for example, in that case, did you notice the Z value to calculate the interval within which the true error has to fall into? It is plus or minus 1.28. So on this side, it is taken minus 1.28, and on this side, it is taken as plus 1.28. So this is the deviation up to which it can allow within this confidence interval. Up to this range, up to this interval, it can allow for this confidence interval, for the true value to fall into. Okay, so this into this area, you are saying that the true value will fall into. 80% of the time, your true value will fall into this particular range, and 10% of the time it may not fall into this range, and 10% of the time it may not fall into this range. This range, I'm talking about this range. Okay, and that is shown as the tails here. Did you notice the tails of the curve here? So 10% plus 10%, 20%. It is counting to 20%. 80% of the time, the true value falls into this range, and 20% of the time, it may not fall into this given range. It may fall into this range or this range, into the tail side. Means you're taking 20% chance that your machine learning model may not perform according to the sample that is taken. It may behave differently with the unseen data. Okay, that is what you are explaining by using this confidence interval. The generalizability of your machine learning model or your hypothesis is 80% here with the given interval calculated by the Z-score. Got it, students? Now see in this figure. In this figure, we are not bothered about what would the least error. Means what least error it may make. The true error, whether it falls into this range, we are not interested in. We are only interested in whether, means we are setting up a bound on the extreme side. Means the true value should not fall beyond this range. It should fall only within this particular range. In that case, here we have set two bounds, lower bound and upper bound. But in this case, lower bound, we are not setting any interval. But on the upper bound, we are setting an interval. We are setting a limit. Okay? Means up to this extent, you can afford the error. But upon that, you don't want to afford the error of the machine learning model. Error of the hypothesis, you are not ready to afford. You are not ready to take up that error. In that case, you have to change your machine learning models, training sample, or maybe you may want to change the entire learning algorithm itself. That kind of decisions you may want to take. Okay, so your affordability level is only up to this extent. You can allow the true error to fall into this range, but not beyond this. Okay. Now to summarize, if a random variable y obeys a normal distribution with mean mu and standard deviation sigma, then the measured random value y of the random variable y will fall into the following interval n% of the time. 95% of the time, 80% of the time. How do you calculate that interval? Mu plus or minus Z-score multiplied by the standard deviation. Okay, or equivalently, the mean mu will fall into the following interval n% of the time. If mu is given, you can calculate with y. If y is given, you can calculate with mu. So how you write this? Y plus or minus Zn multiplied by sigma. Either way you can calculate. Okay, that will give you the interval, that will give you the tolerance level up to which it can afford to make the error value fall into, after which it can't afford the error, right? So we know that the sample error follows a binomial distribution with mean value. What we assumed the mean value to be? The mean value as the true error and standard deviation given by this equation. We have derived this, right? Standard deviation of the sample error is nothing but square root of the sample error multiplied by 1 minus sample error divided by n. Now, secondly, we know that for sufficiently large sample size n, this binomial distribution is well approximated by a normal distribution. If you go on increasing the size of the sample, what a binomial distribution will tend to follow a normal distribution, that is the bell-shaped curve. You go on increasing the number of samples, most of the time it tends to follow this normal distribution. Now, third equation, this equation tells us how to find the n% confidence interval for estimating the mean value of a normal distribution. When we take this mu and take it as 0 and the standard deviation of 1. Now, when you have decided on a confidence interval, based on the Z score, you can calculate the interval up to which it can afford the up to which it makes the true error fall into this particular range, and beyond this it can't afford any errors to happen. Therefore, substituting the mean and standard deviation of the sample error yields the following expression for the n% confidence intervals for discrete valued hypothesis. Okay, so this we have already derived in the lecture 2 or 3. Sample error plus or minus Z score multiplied by sample error into 1 minus sample error divided by n. This will help us to calculate the interval within which the standard deviation of the error may take place. Okay, when you take the normal distribution like this and you have taken 95% confidence interval, now from the mean, normally you tend to observe that the true error falls within this range only. That interval can be calculated by using this formula. Got it? Now the confidence and now let us see what is two-sided and one-sided bounds. If we apply limitations on both the sides, and if we apply limitation on only lower bound or the upper bound, what will happen? Let us see. The confidence intervals can be one-sided and two-sided. Sometimes we can take the confidence interval like this, taking on both the sides, bounded on both the sides, or we can take a confidence interval like this, only bounded on this side, and this side you are not specific about the limitation. That is called as one-sided confidence interval, one-sided bound. Okay, so example, what is the probability that the true error is at most according to an upper bound? This is called as one-sided test. Listen carefully. What we are trying to do here, we are trying to find out the probability of this true error taking the utmost bound as u. Means you wanted to see up to which range maximum error is allowed. This true error falls into which maximum range. But though the true error's minimum value is as low as possible, you are not bothered about that. You are interested only on the maximum range. Okay, so when you take a distribution like this, you are interested only on this maximum limit. You are not interested on this lower limit. Means though your true error gives some lower prediction error, lower estimated error than your sample error, you are not bothered about that. But you wanted to see what is the maximum error up to which it is allowed, beyond which it should not fall into. Okay, that is called as one-sided bound. You are giving the limitation only on one side, right? So any two-sided confidence interval based on a normal distribution can be converted to a corresponding one-sided interval with twice the confidence. Okay, now in this case, observe in this figure. In this figure, I'm saying on the lower side I'm not bothered, but on the upper side I'm bothered that it should not fall beyond this particular interval. So instead of 95%, now I can make my confidence interval as 97.5%. Because before the tails shared actually 5%, right? When I'm taking 95% confidence interval, the tails shared 2.5% and 2.5% on either side. See, whenever you're taking a confidence interval like this, taking this as 95% confidence interval, now remaining 5% error, 2.5 falls in this and 2.5 falls in this range, right? Now when I'm not bothered about this range, I'm increasing my confidence interval till here. So this becomes 95% plus 2.5%, which will give me 97.5%. Okay, so my confidence interval has increased on the lower bound side because I'm not bothered about the lowest estimation error it makes. But I am interested or I am bothered about the maximum range beyond which it should not fall into. That is why I'm stating with twice the confidence interval. Before it was 95% and 2.5% and 2.5% is outside the interval. Now on the lower side, this 2.5%, I'm very flexible about it. So that is added to my confidence interval, which makes my confidence interval larger by making it 95% plus 2.5% into 97.5%. Now my confidence interval increased. So my confidence in the my confidence in the machine learning model about its generalization increased now. Okay, and only 2.5% of the time I'm not sure that it may not predict well. I'm sure, that it may not predict well. Only 2.5% of the time I'm doubtful about the performance of my machine learning model, that it may not predict well with new data. 97.5% of the time I'm confident. Did you get this? So any two-sided confidence interval based on a normal distribution can be converted to a corresponding one-sided confidence interval with twice the confidence. Okay, so that is how you express that. Let us see. That is 100 into 1 minus alpha percent confidence interval. Here my alpha is called as level of significance. Okay, this alpha, when our confidence interval is 95%, alpha is how much? 5%. Okay, listen carefully. Alpha is level of significance, means what risk I can bear with my hypothesis, what risk I can bear with my machine learning model that it may not generalize well with unseen data. That is 5%. When I take my confidence interval as 95%. Now, when I take my confidence interval as 90%, alpha becomes 10. When I take my confidence interval as 80%, alpha becomes 20. Did you understand now? So that is 100 into 1 minus alpha percent confidence interval with lower bound L and with upper bound U implies a 100 into 1 minus alpha by 2% confidence interval with lower bound L and no upper bound. So what is alpha here? For 95% confidence interval, 5%. Now alpha by 2 will give you 2.5%. And that is your lower bound when no upper bound is given, or that is your upper bound when no lower bound is given. That is called as one-sided bound. Did you understand, students, or you want me to repeat this again? This is very, very important. Whenever you're framing your hypothesis, you have to frame your test, whether it should be a two-sided test or one-sided test. Now, if you are flexible with either lower bound or upper bound, you can make it as one-sided test. But if you want to limit it on either side and wants your estimate to fall within a particular confidence interval, then that is called as two-sided test, right? So when I'm taking the alpha significance level as 5%, when 95% confidence interval is being considered, did you understand how we are taking level of significance? If the confidence interval is 95%, level of significance is 5%. Alpha is 5%. If your confidence interval is 85%, what is the level of significance? Students, if your confidence interval is 85%, what would be alpha, the level of significance? Are you listening? When your confidence interval n is 95%, your level of significance alpha will be 5%. Now, when your confidence interval is 80%, your alpha will be 20%. Now, if your bound is a two-sided bound, in that case, this 5% will be shared as 2.5% and 2.5%. Again, in this case also, if it is a two-sided bound, then this 10% is shared as, this 20% is shared as 10% and 10% on either side of the curve, like this. This is 10% and this is 10%, or this is 2.5% and this is 2.5%. Got it? That is called as level of significance alpha. Now, whenever you don't have a limitation on lower bound or upper bound, then we call it as one-sided bound. Now, when we say one-sided bound, limitation on one side is relaxed. Say limitation on this side is relaxed. So your 80% confidence interval will become 90% confidence interval with one-sided bound. That is, only on one side it is bounded by 10%. On the other side, it is not bounded, it is flexible. Right? This is how you calculate the confidence alpha. 100 into 1 minus alpha by 2% confidence interval with lower bound and no upper bound. It also implies a 100 into 1 minus alpha by 2 confidence interval with upper bound and no lower bound, vice versa, right? If you're taking only one tail, if you're not interested in both the tails, then it will be 1 minus alpha by 2 instead of 1 minus alpha. Got it? Now here alpha corresponds to the probability that the correct value lies outside the stated interval. Confidence interval is the correct value lies within that interval, and alpha states the correct value lies outside that interval. That is why when your confidence interval is 95%, alpha is outside that 95%. That is remaining 5%. It is easy actually if you pay interest, if you concentrate. When I'm taking the curve like this, 95% of the time the correct value will fall into this range. My confidence interval is 95%, and 5% of the time it may fall outside this range. That 5% is this alpha, level of significance. Now if you have both sided interval, two-sided bound, then 5% is divided into 2.5 and 2.5. Now if you have one-sided bound, then this 2.5 is relaxed, 95% plus this 2.5% is combined. So your confidence interval is increasing actually. So it becomes 97.5%, and only 2.5% of the time you are not sure about the confidence, whether the true value falls into this confidence interval. It may fall outside the confidence interval. You're taking a chance. Whenever you are promising your friends, how do you tell them? 98% of the time I may come, or 99% of the time I may come. 1% I can't tell. You can't state. You're just guessing the chances of coming to a party. 99% of the time I may come to the party. 1% I can promise you. This one-sided and two-sided bounds are like the area you can't promise. 95% of the time you can promise that the correct value falls into that range. And 5% of the time you are not promising that it will fall into that confidence interval. It may fall outside the confidence interval, 5% of the time. Okay, the chance you are taking is called as level of significance, which is denoted by alpha. Did you understand clearly? Now let us take an example. It will be very clear for you. To illustrate, consider again the same example in which hypothesis or the machine learning model commits 12 prediction errors over the sample of 40 data points, independently drawn samples. Okay, this leads to a two-sided 95% interval of, how do you calculate the interval? I have given you the formula, right? Sample error plus or minus critical value Zn multiplied by square root of sample error into 1 minus sample error divided by n will give you this 0.14. Okay, that interval. Now this leads to the confidence interval with this standard deviation. Okay, now in this case, what is your how is your confidence interval represented? 100 into 1 minus alpha. And what is your alpha here? 90 is 1 minus 0.95, and that gives you 0.05. That is nothing but 5%, right? So when your confidence interval is 95%, alpha will be 5%, but represented in the form of probability, it is 0.05. Means, last time I'm asserting on this, listen carefully, 0.95%, 0.95 probability is associated with your confidence that the true value falls in this particular range, right? And 0.05 probability you're assigning, you're taking a chance that it may fall outside this confidence interval. Did you understand? I'm just explaining the concept in different terms. Instead of percentages, I'm using probabilities, that's all. When I take percentages, 95% is the confidence interval and 5% I'm not confident. That true value falls within the confidence interval. It may fall outside the confidence interval. But if you take the probability, 0.95 probability is assigned to the true value falling into this range, and 0.05 probability is assigned so that it falls outside this particular range. Got it? Thus, we can apply the above rule to say that 100 into 1 minus alpha by 2. If it is a two-sided test, two-sided bound, then it is 100 into 1 minus alpha by 2. What is alpha? 0.05. So when you take 1 minus alpha by 2, your confidence interval now increases to 97.5% from 95%. Because 5% is shared as 2.5 on lower bound, 2.5 on upper bound. Now lower bound, there is a relaxation. So you are adding that confidence interval to that lower bound, 2.5. So your confidence interval now becomes 97.5% confidence. That true error is at most falling into this particular range, that is 0.44. Making no assertion about the lower bound on this true error. Okay, on the upper bound, it falls within this interval, 0.44. And lower bound, you're not making any assertion because you have released the bound. You have made it flexible. It can take any lower value, but on the upper bound, it should not cross 0.44 based on the interval calculated. Now, either way, in the other way, if you find it is 0.30 minus 0.14. In that case, you are making an assertion on the lower bound, but you are making no assertion on the upper bound. Okay? So in that case, also it is same, 0.30 minus, but it becomes minus 0.14. To calculate the interval on the lower side, you have to give 0.30 minus 0.14 when no upper bound assertion is maintained. Now, to calculate the upper bound, when no lower bound assertion is maintained, it is 0.30 plus 0.14. It will give you the positive interval, right? Thus, we have one-sided error bound on this true value with double the confidence that we had in the corresponding two-sided bound. In two-sided bound, we have only 95% confidence. But in this one-sided bound, we are increasing our confidence to 97.5%, stating that 97.5% of the time, my machine learning model is generalizable. My hypothesis performs very well. Even the true error also falls within this 97.5% interval only. But 2.5% of the time, I can't promise. It may make some extreme errors 2.5% of the time. Lower errors you're not bothered about. Extreme errors 2.5% of the time it may make extreme errors, but 97.5% of the time it falls within this particular range. Sample error and the true error will be the same. You're stating with confidence. How much confidence? 97.5% confidence. Did you understand now what is confidence interval and two-sided and one-sided bounds clearly? In the next coming session, we'll discuss on a general approach for deriving confidence intervals. Any doubt in today's class, students? Is the concept clear for you? Pratibha, Vishal? How is the concept? Are you able to understand the purpose behind this confidence interval, two-sided and one-sided bounds?
Yes, ma'am.
Yeah. Thank you. Then we'll meet in the next class. Bye.